Good evening, everyone. We're going to get started here in just another minute or so. All right. Good evening. My name is Melissa GirmScheid. It is 7 o'clock, and I'm going to go ahead and we're going to get started. I am recording this so that if there's anything that you need to go back to later, I will send out the link to the recording with an email that has some follow-up information from this. But feel free. We'll have some time to answer questions at the end. So if you do have questions, please feel free to kind of put them in the chat, or there is a time for questions devoted at the very, very end. On behalf of STEM Teachers Phoenix, I wanted to welcome everyone tonight. Thank you for this. This was one of the sessions at AMTA's Connect Ed a few weeks ago, and it had there was a lot of want for this follow-up to this. I am, a little bit about me, I am a physics first teacher here in Phoenix, Arizona. I teach at West Point High School and part of a school within a school, a leadership academy. So it may sound great, but my students really, they are the very typical high school student. They and their parents have decided to devote themselves to learn some leadership skills alongside their academics. I became part of this project, the Computational Modeling in Physics First, with Bootstrap in 2017, as part of the curriculum development workshop back then. And I've been a part of this National Science Foundation funded project since then. The whole reason behind bringing in computational modeling into the physics classroom is really this focus from the next generation science standards that we are going to use mathematics and computational thinking. And that computational thinking piece is bringing a more modern flair to what we already do in the classroom, encouraging students to think in algorithms and steps and processes that would allow them to solve problems. It encourages students to approach things much the way a computer would. So we want them to automate these processes and do more complex solutions by using the computer and thus computational thinking. So to start off, and I wanted to show you really what the computational modeling approach, how we differ from mechanics. And so this lab is something that most physics teachers do as part of their kinematics unit. Very simple, we have one of the tumble buggies moving across, this is the counter in my classroom. And this is how I start my constant velocity unit, by having students observe the motion of this tumble buggy. And so those of us who have been teaching physics for a while, we get set and kind of how we are going to approach this particular unit and this particular lab to start it. And so what I'm curious about is I want you to think of what are students looking at in this particular lab? What are they examining? What are the variables that they're going to be looking at? What's the goal? What do we want students to get out of this? What do we want them to see as a result of examining the motion of this tumble buggy? And then what representations would come from this lab? Okay, so I'm hoping you have this idea in mind. When you sit down with your students and they determine what exactly they're going to examine in this lab, what variables there are, what do you know the goal, you know what they want out of it, and you know what representations the students should be creating as a result of this. So the computational modeling approach might be a little different from what you have. So these are two of the whiteboards that my students made after looking at this particular lab earlier in the year. So both of them created these whiteboards as a result of what we collected. So when I do the tumble buggy lab with my students, we're listening to a metronome, and the metronome is ticking every 2 seconds. And so the students are recording the position of the buggy every tick, every 2 seconds. Now, I want you to keep in mind, I do teach 9th graders, so please be kind when you see there might be a few errors in here. There's some very 9th grade errors on their whiteboards. But this is how they're analyzing the motion of the tumble buggy. Every tick, we use receipt tape, or it could be like an adding machine tape, or one of the best ones, one of the suggestions that came from one of our former workshop participants was taking the big roll of brown paper towels that we all inevitably have in our classroom and unrolling it, make a large number line out of that. And every time they hear the tick, they're marking where the buggy is. So they are marking the position for every tick. And this is our next step. So this is what we're using to facilitate discussion within our groups. And so from that, the students are looking at what exactly is happening. They want to look at patterns. And so knowing that I need to get my students thinking computationally, I want them to think in iterations and patterns. And so as a result of looking at these iterations, patterns, this is our next step. So we're looking specifically, does the data follow a pattern? And so on the left, you can see these are the next whiteboards that my students are creating. On the left, this group has created a series of state diagrams looking at the motion of their buggy. And on the right, this was another group that chose to put their data table onto their whiteboard and take a look at the pattern. What's funny about this is in discussion, the team on the left came around to determine that they actually had their buggy was following a pattern. The team on the right decided to add in their state diagrams later. So both were able to approach the problem with a couple different representations as a result of collecting data, and then ultimately during discussion inform each other that there was a pattern forming in this motion. And that repeated pattern is where the computational piece comes in. So this is another buggy, although this buggy looks a little different. If you look closely, you're not going to see the buggy's wheels turning. It's actually a picture of a buggy. And the picture of the buggy is being controlled by a function. So this function, this functional language that we use within the computational modeling, this functional language is allowing the students to then take that pattern and recreate the motion of the buggy. And we do that through something called a function design. The function design is yet another representation of what's happening with the buggy. Now I want you to pause for a second. If you look at this, we have not yet graphed the motion of the buggy. It's because before my students actually see a graphical representation, I want them to deeply analyze the motion and what exactly does it mean for something to move. And so by looking at that pattern, how the position changes for every tick, they're able to determine what exactly what it means for something to move and how we can recreate that motion. So these are examples from the same group of students of what we call a function design. And the function design, I can kind of show you what this means here. This top, I would read this next x is of type number producing number. Next x is the name of our function, is of type, its domain is a number, and the range is a number, or input is a number, output is a number. So part of teaching using this computational modeling approach is that students are getting a much more in-depth introduction to functions. And they're, for my students, getting the introduction before they get introduced to functions in Algebra 1. So this is bringing in an additional piece where they're learning functions from a manner that's going to give them some visual feedback. The next piece is what we call an examples block. And so you can see that next x is our function name. It has an input in parentheses, and then they are showing the calculation of how we determine the next x, the next position. On the left, that group, I can say that when they get to that visual output, when they put in the computer, they're going to see some things that don't quite line up with what they expected. Their pattern is not quite following what's needed. But the nice part is they're going to get visual feedback. Computational modeling allows the students to not only test their problems by working through them mathematically, but they're also, because their program is simulation, they're also getting some feedback visually. Now, my group on the right expanded upon their work and showed the calculation itself. Part of what my students always hear is, why are you doing the math when the computer can do it for you? And I encourage them to use those calculations and allow the computer to do that math for them. And that's completely by design, because computers are a tool that can allow them to perform iterative calculations over and over and over again. And we're trying to make the case for students of why they need the computer. And we do this, mind you, this is unit 2. We've made the case back in unit 1. So my students, I'm looking at the right, they have examples block, and then they have what we call a function block. And that function block, you can see, takes an x as an input. It's making a general version of the function that can then be evaluated for any value of x. Hey, this is what it looks like when the students get to the computer piece. So we've designed our function on paper, and then went ahead and opened up. This is what it looks like when the students get on the screen. There are instructions for them. So the students are not programming from scratch. There is a background code that has been designed by the workshop and curriculum development team, along with our team from Bootstrap. Bootstrap is an organization out of Brown University that has focused on, they really started as mathematical integration of mathematics and computer science to teach students, again, to teach functions much better, and to integrate some computer science to provide that equity. Since all of our students are in math class, and not all get computer science, often computer science within math class makes an equitable experience so any student can have that access. And so through Bootstrap, they developed this language called Pirate. And if you see at the top left corner of the screen, there's a little red and blue pirate that looks like it has in bones a lambda symbol underneath it. Really good reason for that. Pirate, if I put it together, it's Python and Racket put together. And the Racket language has a red and blue lambda symbol as its logo. And so by putting that together with the name Pirate, now we have this red and blue pirate skull with the lambda symbol in the basically crossbones underneath it. So Pirate is really designed for students. They get great feedback. We can make it very student friendly. It has all the colors here actually correspond with Expo marker colors. So there's a lot to it that has been fabulously designed by the team at Bootstrap and continuously upgraded for our needs. So this is what my students see. They've created this function design on paper, then on their whiteboards, and now they're going to put it in the computer. And I did kind of make a version for you that the URLs at the bottom right. I'll also send it in an email later, but this is what they're working with. They're able to change how often the buggy is moved, that delta t, change in time. So that tells it how often that calculation is going to be made. They're able to move their buggy wherever they would want. Because when I have my students do the lab, they all start at different locations and they go different directions so we can see different things. They are able to set up their examples just like they did on the whiteboard and paper before that, and then they set up their function. And hopefully from that, what they're going to see is they're going to see the motion of their buggy match with what they saw from the motion of the buggy in the lab. So they should see it be comparative. So that initial one in the computer, we set it up so they're moving the buggy every 2 seconds, just like the metronome tick. And again, we haven't graphed anything here. We're still looking at these patterns, these iterative calculations. So my next step with students is then we sit down and we look at what would happen. These long rectangles that they're drawing on the whiteboard represent the receipt tape that they were taking their data on. What would happen if we change that delta t? And so each one of the rectangles is representing a different delta t. So they start off with 2, and then I ask, well, what would happen if we made the delta t 1? And so I can see the group on the left, their thinking process was interesting to me. And I took this picture because initially they said that their delta x, their change in position, was 12.5 centimeters every 2 seconds. They had a really slow buggy that I had manipulated. And then when they changed the delta t to 1, they put these red dots in between their original green ones. And they said that the delta t is still going to stay 12.5. And I remember this group, they had a great conversation in their group and they said, wait, that can't be right. Because they were seeing that it wasn't quite lining up. The second rectangle, the dots were not lining up with the one on the top. The group on the right looked at it initially and said, and they had a much faster one. Their delta t was 85 centimeters for every 2 seconds. So when they set up theirs, they had a great conversation. You can see what they drew it in, and they kind of drew it wrote in a different color. It started with 85 for delta t of 2, and then they originally wrote 85 for delta t of 1, and they went, wait, that can't be right. If the car is moving 85 centimeters for every 2 seconds, then for every 1 second, it's only moving half that. Again, focusing on these patterns and these iterative calculations with students. One part that is fantastic by doing that is it brings motion maps to the forefront. So motion maps are a much more, they're much more prominent representation in the computational modeling resources. Motion maps are very concrete, especially for my 9th graders. When I started with the development workshop, I was still teaching juniors and seniors, and this worked great with my juniors and seniors too. Because I found what happened is they relied so much on the mathematics portion that they were losing some of the concept. So by bringing motion maps to the forefront, the concept came back to the forefront. So we really got into this pattern forming and what exactly was going on here. And so it produced a new depth of understanding with my students. So this is a later simulation. It happens after the buggy. And you can see that what they're doing on the left, they're seeing this dog move along. The students use their programming skills to move this dog, and the computer's actually producing a motion map for them. So before my students truly draw motion maps themselves, this is what they're seeing. They're seeing the computer output these motion maps. So then we're able to determine, what do the dots mean? What do the arrows tell us? What does the gap between the dots tell us? And again, focusing on those patterns. Later, in the beginning of our uniform acceleration unit, we're building on this differential model. Now, we built it by talking about iterative calculations. We're really talking about the difference in position and encouraging students to go from using a delta t of 2 seconds down to one of 20 times for every second, where they're moving something fast enough to producing that smooth motion like an animator would like. Using a simulation moving the buggy every 2 seconds produces a very jerky motion and nothing that's satisfying for students. So being able to create something that's smooth and has a nice animation that where the eye really can't pick up that something is moving in chunks is very satisfying to students. And so by the time we get to uniform acceleration, now we're making some changes. We're still using those chunks. We've made that difference in position for every tick. We've made it really small, but now I can also change the velocity in these little chunks. So I want you to think about if I'm making a curve, a quadratic function, and I take that quadratic function, I can actually make it a series of line segments. And if I make if they make the difference in time really small, those line segments get shorter. And instead of having something that looks like a series of line segments, it starts to look more like a curve. And that's what the students are programming. So here, this is an example of something that we do with the students in uniform acceleration. So this is a pace car simulation. The car at the top is the yellow car, it's a pace car, and it's controlled by the background code. The cars in black, blue, and orange underneath it are controlled by the students. So in this, they're using their knowledge to keep up with the pace car. And so let me run it for you and show you what exactly is happening here. So this is moving the car every second. And what students are doing is they're using their same function for next position, next X, that they built in Unit 2. But this time around, they also have to change the velocity. And so they're using similar patterns for this. And in this one, this is actually a tricky way of teaching them the area under the curve and how that relates to a changing velocity. And what they're doing is determining which velocity are they using to calculate this. The one in black here is using the current velocity, the velocity at each tick, in order to change the velocity of the black car. The one in the middle, since the one at the top is falling behind, the one in the middle, the blue car, is using the velocity at the next tick to determine what the velocity of that car would be to move it along. And students are seeing it go way too far. The one at the bottom is using the average velocity over the interval of time to determine how far that car should move. It's very intentional that that bottom car is not exactly the sportiest one, but it's the one that keeps pace. So students are programming this entire thing. So rather than just doing these problems on paper, they're actually putting this into the computer and then able to visually see what's going on. And it leads to really rich discussion. The advantages of doing this is students are thinking in small, little, tiny, they're different in those differentials and very small calculations. So our students do go from thinking moving something every 2 seconds to now I'm going to move it every 1/20th of a second. And because they're doing that, they're also using they've understood that the computer is a very useful tool. This increases their use of functions. So my students don't ever use an equation, a kinematic equation. They're using kinematic functions. And I have 9th graders using kinematic functions. They understand that it's taking in an input and producing an output. And what I'm hearing from their math teachers is that by the time they start functions in algebra, they really truly understand what the difference between domain and range is, how I evaluate a function, how to evaluate a function within a function. And so it's bringing that to the forefront and having them practice that more. When Bootstrap was originally formed, part of that is there was looking at research in mathematics education and seeing that functions was where mathematical understanding there was a gap between where kids were before that and where they were after that. In other words, what was happening is functions were really causing a conceptual block, and it was hard for students to get over. Even though I know that for years teaching math, I would always teach my students equations. Okay, we're going to look at y equals mx plus b, for example, and then switching to f of x equals mx plus b. For some reason, that was throwing them off. So this is allowing them to use functions more, get that practice, so that when the functions come across in algebra, they've already seen it. They've got practice with it. They know what that means. The other thing is immediate testing. So right away, instead of doing a problem in a worksheet and then asking me, is that the right answer? They're programming something, putting it in a computer, seeing what it does, and then determining if that was what they meant. Really common in the tumble buggy one, when they're recreating it, is students do little things like it moves in the wrong direction. And so having them look back and determine that their velocity needed to be negative when they put in positive. So it gives them that immediate feedback. And probably the most important one, and the one I enjoy the most, is this gives a lot of error analysis and problem solving for students. Pirate, the language is designed in a way that students don't get error codes, they get feedback. It tells them, it highlights the section, and I'm going to show you in a second. It highlights the section and tells them not what to do, but tells them where they probably should look, or gives them some feedback that really asks them to do something a little bit differently. And I know as well, because Pirate is a language that is constantly being upgraded and redesigned and made extremely better. They have some things coming down the road I would love to tell you about, but I can't. But there are some things coming down the road that are really important and going to be kind of game changing for the teachers that use this. So here are these error analysis. So this is part of what makes this so powerful for students. And my students, we started doing this in August, and now in February, they are actually helping each other look at errors, and they're really good at reading this. So on the left, this is what happens, why my students make those examples blocks. So it asks them to look at their examples block and then compares it with the function to see whether those two things match up. So you can see, like on the left side, on the left of the screen, it has this thing where it only succeeds if left and right sides are equal. So it's comparing what they wrote in their examples, what they believe should happen, and what they wrote in the function to see if those two things match up. On the right, I've put some examples of things that they might have. So one of those, they're getting something where the domain, the contract, does not match up with what they said. So they've given it two different domains, and the function can't have two different domains. There's some instances in the middle one where their capitalization was not correct. It's really great at making the students super meticulous. And then the very bottom one, they just didn't fill in the information. So it does, because Pirate will give them this feedback, it does ask them repeatedly to kind of check their work and see how they're doing. I see a great question. Thank you, Jane. So Jane asked, what are the minimum technical requirements for computers? So Pirate is Google-based. So as long as students can access the internet, they can work on Pirate. My students have, I'm trying to think what they had before, because they just got new computers for all the freshmen in our school. the older ones were Lenovo ThinkPads or something like that. I've used these on old school computers that were probably 8 or 9 years old when I was teaching juniors, seniors. But it is web-based. It's Google-based. If Google schools have a little bit of advantage because students can actually save their programs to their Google Drive. For my school, we are a Microsoft school, so I've kind of found ways to work around that. But it is something that is easily accessible. It does not have to be downloaded. And therefore, usually we don't have to worry about any of the, like downloading issues, anything. I don't have admin privileges. No, it's all on the web for students. One of the other advantages that we have of computational modeling, because my students are thinking in small little pieces, thinking in those differentials, is we can look at some really challenging scenarios. And these are 3 of my favorites. I made the slides. I could just choose my absolute favorites. So on the left, one of the cool things that I do when I teach my students free fall is this is the video from the Apollo 15 hammer and feather drop on the moon. And so you'll see there are red and blue dots. They're following, the red and blue dots are background code following the hammer and the feather. My students actually use this video to determine what the acceleration in free fall is on the moon. So they're going to collect a lot of data and then use that data to determine the acceleration, and then use what they know. They're programming the circles around the dots. So they're programming how that's dropping. So they're able to check their acceleration that way. On the right, on top right, is like my absolute favorite, which is a self-driving car. So in this, students have to program a self-driving car that's going to stop at a safe distance from the stop sign. And so this is one of the sneaky ways that we teach one of the kinematic equations without ever teaching the kinematic equation. Students are challenged to use a velocity time graph and find the area underneath and create a function from that. This lends some really great conversations and discussion within the classroom. And then the one on the bottom right is a drag race. So students are in these resources in computational modeling. We're looking at air resistance more. So the students are actually programming some drag on the car as it moves there, and then they're going to program some drag on the car as it releases a parachute. So with that, we're teaching them conditional statements in programming, which lends to piecewise functions in math. So one of the things I absolutely love is now I have the Algebra 1 teacher coming to me and say, did you teach piecewise functions to my students? They absolutely did. They learned how to program a drag racer because they were able to release parachute at a certain point in time to create more drag on the car. So they're really putting this math practice into a visual format. Okay, I'm so glad we're going to have time for questions. What questions can I answer from all of you? Feel free to put it into the chat or raise your hand, and I will absolutely see that you have your hand raised, and I can call on you if you have questions. So I see, how young can you teach this at? So, I mean, I teach this to freshmen. The resources were designed for 9th graders because they're designed to go along with Algebra 1. We do have some teachers who took the computational modeling workshop and are using this with 7th, 8th graders. I don't know that we've had anyone who has done this with any grade lower than like 7th, 8th grade. Bootstrap itself does have a program that does algebra. They have Bootstrap Algebra, where they're using some of these things. And I know that we've had some teachers who've gone through the computational modeling workshop and have integrated Bootstrap Algebra and Physics First. With 6th graders, I would probably, it would depend on what they are doing in math. This does require them to have some degree of algebra knowledge and kind of build it together. It is designed to deepen their algebraic understanding. So it would probably just depend on what the 6th graders are doing in their math classes and also if the physics concepts would be something that would fit right in with what they're doing in science class. What other questions do you have out there? Yes, it can be done using iPads. In fact, one of the workshop developers and curriculum developers, one of my cohort for my partner in crime for a few years now, has iPads at his school, and he does accomplish all of this using iPads. Probably the only thing, actually, no, I'm going to take that back, because we had something in one of the simulations that used a pause function, a space bar, and we took that out because it was not working with iPads. So this is all ready to go for iPad schools. What other questions can I answer for you? What math teachers would benefit from PD in, say, units 2 and 3? Oh, absolutely. I would say all of them. All of them. I have colleagues, coworkers from Algebra 1 up through Calculus 1 who have seen what we're doing, and I tell my students it's sneaky math. We've sneaky math everything in there. The professional development, to take the computational modeling workshop, we've had math teachers take the workshop before and have found something for them, and we're always looking for feedback to kind of help out. We love having math teachers in the workshops, because then we can get some ideas of how better to marry those two together. And for just the pirate piece, Bootstrap has algebra and data science. There's probably more, and I'm probably leaving something out, but algebra and data science to look at the mathematical piece. And I know that we've had some good success with schools that have had their math teachers do like Bootstrap algebra, and then their physics teachers are using computational modeling and kind of putting them together. It is easy. I will. So for computational modeling, physics first, there's a couple things that we recommend. Number one, all the materials have teacher notes that go with them. But to get access to teacher notes, these are through the American Modeling Teachers Association. I will send out information in the email afterward about how to find those materials. But major benefit of being an AMTA member is that those teacher notes are there. And we have worked diligently on making sure those teacher notes are almost, I don't want to say step by step, but there's even discussion goals, what should you be doing every day. We do offer workshops in computational modeling. There's going to be one at ASU, one at Baldwin Wallace in Ohio this summer, and I can't say where, but it looks like we should have, by the end of next week, we should have a location on the East Coast. That would be my ultimate recommendation for being able to use this with your students, is training is so important. Our computational exercises available separately to use. They can be used separately. It honestly would not be something I would suggest, because they are kind of integrated into the curricular resources. There are links in the resources themselves. Are many schools adopting computational modeling? We do have schools across the country. I'm trying to think if we've had anyone international. Yes, we have someone who is with DODEA. But we have schools all across the country. Like I said, we did the curriculum development in 2017. Our first workshop was in 2018. So we've had really one workshop a year since then. This is the first year that we're not going to be a grant funded workshop, and it's expanding. So instead of the three of us who have led workshops together, being together, we're leading separately, hence the 3 different workshops. So we're still bringing it to more teachers. We would love to have more teachers involved. And of course, that's why we do this. And that's why we're going to lead workshops across the country. What else can I answer for you? What content or how much content you're able to cover in an academic year? Okay, so with computational modeling, right now, we have 5 units working on the 6th. So my students, the units that we use are have the computational piece in it are qualitative energy, constant velocity, uniform acceleration, balanced forces, unbalanced forces, and we are working on momentum. My students are the alpha testers actually this week. So I'm in so the 6th unit this week. So, and then I'm gonna wrap up before we get to spring break. I'm deviating from what we have in the computational because my students are done with it. So honestly, me as a computational modeler, I then use some other computational pieces with my students. We'll do some Excel spreadsheet programming because they need it for future classes, and also probably some Sonic Pi with our sound unit. So I want them to keep up the computational piece because it's great practice for them. I get students who are very interested in the coding, and I get students thinking in iterative calculations, and I just keep them kind of thinking at that higher level. So I do get through this content. This is not an all year for me. I do see my students every day though for 55 minutes a day. So the schedule does make a huge difference there. So if high school math teachers coming to the week 1 of the computational modeling and mechanics course. So it could be included in the math course. My suggestion would be if math teachers wanted to include it, to come to the entire workshop. The reason being is that to include this, we don't teach the coding right up front. So it doesn't teach, like we teach all the coding and then you're good to go. The workshop that we do, the workshops that we put on at ASU and at Baldwin-Wallace, and the one that will be East Coast, it very much includes the computer science learning along with the physics learning. They are 100% integrated. You can't really pick them out. So the students are learning the computer science pieces as they go. So I say with math teachers wanted to learn the language, then you want to go to like the bootstrap algebra. And those you'd have to go to bootstrapworld.org. I'll include that in my follow-up email as well. And from bootstrapworld.org, they offer workshops across the country, I believe. And you can actually have them come to your school if you wish. Do you want to bring that back in case? What other questions can I answer for you all? Oh, no, that's great. So it does in my 9th grade curriculum also cover earth science to satisfy? No. Only reason being is that where we have covered the space science standards. Arizona is not an NGSS state. We are an Arizona Science Standard state, but they look an awful lot like the next generation science standards. But we've included space science basically because we can weave in the physics with it. We can use what we know about the physics to explore the astronomy side. My school also, we're lucky enough to offer geology class. And so all of the earth science standards and the space science standard, earth and space science standards are covered in that geology class. There's a few other things that are covered in like the ecological ones are covered in biology, and some of the ones that can be under chemical science are covered in chemistry. So I don't have to do all of them. Are there lingering questions out there? I'm going to put this up for you. We do ask STEM Teachers Phoenix, always ask, we would love feedback from you so we can make these STEM salons better. And then we do have upcoming future sessions, and I'm going to send you some information about the computational modeling ones specifically. Those workshops that are coming up through the American Modeling Teachers Association over the summer. And STEM Teachers Phoenix has a couple more of these STEM salons that are available to anyone across the country. Next week, there's one on technology in early elementary with a teacher that actually teaches computer science for K-4, which I absolutely love that students are getting that early. And the first week of March, we have Rebecca Vieira from PhET joining us to do an introduction to PhET simulations. I think that one will be amazing. Anyone who wants to include those simulations in their classroom, math and science teachers, those are, if you've never looked at phet.colorado.edu, it's phet.colorado.edu. If you've never looked at simulations there is a treasure trove of stuff that can be used that actually embed really well into a lot of learning management systems as well. So I will gladly continue asking if you have questions. I'm happy to answer those. If not, I will send you all a follow-up email just to give you some additional information if you would like. And then, and also for my ASAP fellows, that hour professional development, you'll be getting a certificate, and I will send that to Shala as well, so you get that. I apologize, I'm going to put that right back. Thank you. Thank you for joining us this evening. Oh, ASAP stands for the Arizona STEM Acceleration Project. And it is grant funded from the ADE. It is designed to provide professional development and support to teachers of STEM across the state. Thank you, everyone. Oh, awesome, Jane. I will make sure I put that link in I'm going to do my kid version here and take a picture of the link, and I will send the link out in the follow-up email. Thank you, everyone. If you have questions, you want to stick around and ask them or pop them into the chat, I'm more than happy to answer those.
Hi, can you put up the link one more time? Absolutely. I was trying to do the survey and it's just kicking me out.
Oh, no problem.
Thank you.
You're welcome. I did record it. In fact, I'm going to stop